is I want to discuss the systematic study of gauge group parameter space of the free fermionic heterotic string landscape. I want to go through a systematic process that we've developed at Baylor to have total control of the models that we're evaluating so that we don't have any unknowns. We have correct weighting probabilities of the models that we find. We consider degeneracy factors, uniqueness of models in particular, as I'll get through. And then if there is time at all, I'll also talk about some of the research that we're doing on phenomenological studies of extensions of the Nahi-based model, and also a variation of the Nahi-based models that we found and been working on that we found work very well in producing mirror model types. And then a series of papers that the research is based on. Again, the free fermionic heterotic model building process has been known for quite a while. I just have a quick review of it there. I don't want to spend much time on it though. Again, the degrees of freedom that we're using are worldsheet fermions. I'm going to be talking in the real basis for most of this. This all is pretty well known. I'm going to focus specifically on what we're doing and why on here. What we want to ask, again, as we study the string landscape in a particular region, we want to get some idea of our approaches, the probability of the properties of our universe being found on the string landscape. And we're investigating a focused area that has produced some of the most phenomenological models to date. That is the free fermionic heterotic region. And what we want to ask in our study is what gauge groups are possible, and what is the probability for a given gauge group product, what's the probability for given observable and correlated hidden sector gauge group of factors, what's the probability for a given class of hidden sector matter also relating to dark matter issues, and can the more probable hidden sector matter classes satisfy requirements for dark matter. If another question we ask, if a U1 is present, what's the probability it's anomalous? Because as many models have shown, anomalous U1 critically affect phenomenology of a model, including forcing, flat direction, vacuum expectation values. Prior analysis of free fermionic heterotic string landscape gauge group statistics have focused on order 2, that is just periodic and aperiodic boundary conditions, and by randomly generating these models. And here I'm talking specifically about the research that Dinas et al. Did. There have been some other studies, including by people here, but those have focused on particular gauge group models. I'm talking about models studying probabilities of gauge groups in particular. And one of the issues that occurred with the order 2 randomly generated models, as discussed in those papers themselves, is that the statistics were from randomly generated models that were very susceptible to floating correlations. What's that mean? It means that some models have many more equivalent representations than others, and therefore more likely hit the former models in random searches. One of the interesting aspects that we've discovered is the degeneracy of free fermionic models. In particular, we've gone over several billion models of what I'll classify as gauge group models. And we found within those few billion, there were only on the order about 550 unique models. So there is a vast degeneracy factor in these models. And we're working on process for speed of processing to eliminate redundancy factors, as I'll get to. What we're doing is performing a systematic study of the gauge group parameter space using an efficient linearized re-expression of the constraints, which generally are quadratic, but for free fermionic, we've re-expressed them in a linearized mode, which makes, again, for a very efficient process. And we've defined a process to systematically investigate the gauge group models using limits of what we define as order, that is the layer, the number of independent basis sectors that we have, and the order, the order of the twists of a model. We've gotten to very high order. We've gone up to order 32, and we're doing a complete range. But we've also, in the study of advancing order from 2 to 32, we've discovered some interesting degeneracy issues that I'll get to. Model production and analysis is currently at a rate of 10 to the 12 models per year, with further rate improvements underway. First off, and we've also now are investigating, we started D equal 4, but now that we've gotten through the first order, the initial stage of D equal 4, we're now doing complete analysis of all models in even and odd dimensions for gauge group. and from d equal 4 up through 9, and 10 for verification of some of the redundancies. D equal 4 layer 1, we generated all order 2 to order 32 gauge models. Again, that was on the order about 2 billion with a single twisted gauge basis sector, and from twisting of order 2 all the way up to order 32. Any dimension D layer n automatically includes the all periodic sector and standard SUSY sector. So we're actually talking about layer 3 models. But I'm saying layer in terms of the numbers that we are adding to standard, all periodic sector, and SUSY. And what we're getting out of those, we're investigating models that are purely gauge sector. That means we have the gravity part and gauge part, but no matter sectors. Those are the next step. The interesting part is when we're looking at these models, we're inherently looking at the embedded n equal 4 supersymmetric model. Or if we choose the GSO projections for our layer 1 sector oppositely, then we completely break n equal 4 supersymmetry to n equals 0. This is giving us a range of some of the properties of the models from the upper maximal supersymmetry to the completely broken supersymmetry. And I'll show you how that fits in a couple of minutes. One thing we found, again, as I said that, we've analyzed gauge group models all the way from order 2 up through order 32. Covered billion models, but we've discovered, again, there were only 527 distinct models. 68 distinct models with n equal 4 supersymmetry, and actually then 527 with broken supersymmetry. Interesting thing is there was an overlap of 50 models that had completely matching gauge groups that had the n equal 4 version and also n equals 0 version. We've gone on to layer 2, but interestingly, in layer 2 so far we've discovered no new gauge group models. It's showing quite a bit of redundancy also. And then we've also gone on, as I said, to d equals 6, 7, 8, 9, and then just a test for 10. I don't have time to go into that. And here's the data for analysis of the models. And we're just in the process of doing odd. It's a little bit tricky on how to handle the gravitinos on that. But for the others, at the d equal 4, one thing we're able to see is we get some idea of what gauge groups are possible before matter sectors are added. And that's one thing that's proven interesting. Without adding matter sectors, we're not able to get standard model, which this appears to imply an interesting implication that the standard model gauge group implies the existence of matter also, which obviously is a post-proof. But as I said, we ended up with out of a few billion models, we've ended up generated such a high redundancy that we ended up with just 509 unique with n equals 0 and 68 unique with n equal 4. And among those two, there's an overlap of 50 matching gauge groups between them. And as we might expect, as we go up for higher dimensions, there's less parameter space allowed, so the number of gauge groups, unique gauge groups, cuts down. We see at d equals 6, we had 73 unique n equals 0 models, 18 unique n equal 2 supersymmetric models. We go up to d equal 8, there was 50 and 13 at n equal 1, and some might ask about how we know that n equal 1 supersymmetry can be obtained at d equal 8. There was a paper by Chidori et al. A few years back that worked out the process of how d equal 8 models can provide n equal 1. And then, of course, we have the 6 and 2 for the well-known class of d equal 10 models. One thing interesting, at d equal 4 for n equals 0, in this gauge group search, we indeed found a model that has SU5 and E6. Yes?
5 minutes.
Okay. This was counter proof of an earlier claim that those two gauge groups may not be able to work together, that modular invariance may kick them out. We have counter proof that they can be. We also found similar models with n equal 1 supersymmetry in our Nahi extension study, which I will not get to. Interesting thing, what I want to cover now is some plots of the distribution and of the gauge group models per order for d equal 4 to 10. As you can see, we have here we have the n equals 0 models, and here we have the n max for a given dimension. What we discovered, interestingly, is again, the higher the dimension, the narrower the range of unique models. And so, example, for d equal 10, we only needed, to get all of the models, we only needed order 2 for the supersymmetric and up to order 6 for the non-supersymmetric. For d equal 8, we have a complete list of the non-supersymmetric, simply stopping at order 14 twists, the supersymmetric, order 6. For d equals 6, you can see it spreads out, and we had to go up to order 22 to get the complete range for non-supersymmetric, and up to order 10 for the supersymmetric. For d equal 4, we had to go up to, we had to go up to order 24. We stopped our plots at 22, but we had to go up to order 24 for d equal 4 models for the non-supersymmetric, and order 22 for the supersymmetric. The interesting thing is, we discovered that there was degeneracy among these models too. And in fact, order 22 for n equal 4, for the n equal 0 models, contained everything. So all we needed to do to analyze the complete set of gauge group models for a single sector for the n equal 0 was look solely at order 22 twist models. Everything below was contained in that. And the same thing for the n max too. And I'll show that in a little bit. This is showing again the new models per order, again for d equal 4 to 10 for the two combined. And you can see again how keeping supersymmetry folds in the number of orders that we need to consider for completeness. It's about double if we go for complete supersymmetry versus completely broken supersymmetry. The order that we investigate has to pretty much double. The other thing we found is, it's interesting, as we go up, on occasion, higher order lose some models. For example, d equal 4, n equal 4. The reds for a given order show the new models that occur, and the green plots below show the number of models that are missing. But eventually we get up to some mode high enough that they include everything. So again, at order 22, that's all we needed to look at. We didn't have to go back. So we're finding a way of efficiently looking at, once we know what the highest twist order that we need to look at is, we can focus on that one and ignore everything lower, because we'll get a complete classification of models using just that twist order. And we found that's true for both broken supersymmetry and unbroken. We also did statistics in our studies on gauge group factors for all of the models. Again, I can't talk in detail about it. We'll have to reference the papers, but we found some interesting distributions of the gauge groups and the number of gauge group factors on these. Looks like I actually have a little time to go on. That's one area of our research, focusing on the gauge group studies at n equal 4 models. And as I said, we're pretty much nearing completion of layer 2 gauge group models. And again, we've seen that these 550 some gauge group models that we got for dimension 4, that we got at layer 1, are the complete list so far. Nothing new. There may be some at higher order too. Higher layer. But it looks like by advancing from simply periodic, antiperiodic boundary conditions to high order twist, we can use low layer models, and we have a vast range of stuff that we're getting.
You're out of time.
Okay. And I think that is about where I thought I'd stop. Any questions then on it? Okay.
Any questions? Did you look at the statistics of matter content and number of family and things like that?
Again, in these gauge sector, there are no matter sectors to it. We're going to be adding that now. But in the other two studies, we haven't investigated the matter sectors. The Nahi extensions and the Nahi variation extensions. There we are looking at matter distributions.
Any particular feature in that respect?
We found some interesting ways of getting 3 generations. By higher order twists, we can get 3 generations by simply adding, in fact, 3 generations to a flipped SU5 by just adding 1 sector on to Nahi. We found out that if we have twist orders that are prime with regard to the earlier twists, we can get by with fewer sectors.
Mm-hmm. Okay. Any further questions? No. Okay, the same case.